Chapter 3, Current Electricity of Physics. Introduction. In Chapter 1, all charges, whether free or bound, were considered to be at rest. Charges in motion constitute an electric current. Such currents occur naturally in many situations. Lightning is one such phenomena in which charges flow from the clouds to earth through the atmosphere, sometimes with disastrous results. The flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in a steady manner, like water flowing smoothly in a river. A torch and a cell-driven clock are examples of such devices. In present, we shall study some of the basic laws concerning steady electric current. In the chapter 1 and 2 we saw charges, we studied about charges, but they were in rest, they are not moving. But in this chapter we will see moving charges. One such example in nature is the lightning, where charges move unsteadily from atmosphere to earth, from the clouds to earth through the atmosphere. And example for artificial currents are clocks, torch, etc. Electric current. Imagine a small area held normally to the direction of the flow of the charges. Both the positive and negative charges may flow forward and backward across the area. In a given time interval t, let q plus be the net amount that is forward minus backward of the positive charges that flow in the forward direction across the area. Similarly, let q minus be the net amount of negative charges flowing across the area in the forward direction. The net amount of charge flowing across the area in the forward direction in the time interval t, then t is q equals q plus minus q minus. Let's read the statements again. Imagine a small area held normal to the direction of the flow of charges. Small area held normal to the direction of the flow of charges. Both the positive and negative charges may flow forward and backward across the area. In a given amount of interval time, let q plus be the net amount forward charges minus backward of positive charges and flow in the forward direction across the area. Similarly, let q minus be the net amount of negative charges flowing across the area in the forward direction. The net amount of charge flowing across the area in the forward direction in the time interval t, when q equals q plus minus q minus. Q plus minus q minus, where q plus is the net amount of charges flowing in the forward direction across the area, normally to the area, where q minus is the total amount of charges or net amount of charges flowing forward direction normally through the area. This is proportional to t for steady current, and the quotient I equals q by t is defined by the current across the area in the forward direction. If turn out to be negative number, it implies that current is in the backward direction. Currents are not always steady, and hence more generally we define the currents as follows. Let delta q be the net charge flowing across a cross section of a conductor during the time interval delta t, that is between times t and t plus delta t. Then the current at time t across the cross section of the conductor is defined as the value of the ratio of delta q to delta t in limit of delta t tending to 0. Let's read the statement again. Currents are not always steady, and hence more generally we define the current as follows, where delta q is a net charge flowing across a cross section of a conductor. Delta q is a net charge flowing across the cross section of a conductor during the time interval delta t. Then the current at the time t across the cross section of the conductor is defined as limit where the change is 0 delta q by delta t. In SI units, the unit of current is ampere, and ampere is defined through magnetic effects of current that we will study in the following chapter. An ampere is typically the order of magnitude of currents in the domestic appliances. An average lighting carries currents of the order of tens of thousands of ampere, and at the other extreme, currents in our nerves are in microamperes. Let's see this paragraph again, or this topic. First topic under current electricity, electric current. When we have an area, this is an area of A, let's assume, and in this area, let's assume charges are moving in both directions, both q plus or positive charges and negative charges are moving in both forward and backward direction. Let's assume this is an area and charges are moving. This is the area, then they are moving, the charges are moving normally, both positive and negative charges are moving in both directions normally to the cross-sectional area. If that is the case, then let q plus be the total net amount of positive charges moving in the forward direction. Forward direction meaning if 1 plus q charge is going this side, let's assume 2 plus 2 charges are going this side. 2 plus q charges are going to the right side. Let's assume in the same cross section, let's assume 1 positive charge is going in the left side in the same cross-sectional area. Then q plus equals 2 minus 1 when we consider charges, the net amount of charges flowing in the right side direction, where q plus equals 1. The same for negative charges as well. where Q minus is the net amount of charge, net amount of negative charges flowing in the chosen direction Q minus is the net amount of negative charges flowing in the chosen direction. That is a few sentences of the in case of steady current, we take Q, the total charge will be equal to Q plus minus Q minus. Yes. If this is the total charge for steady currents, then the current I will be equals to Q by T, where T is the time taken. Electric current, when positive charges and negative charges going in either directions across a cross-sectional area, normally to the cross-sectional area, then Q plus is the total net amount of positive charges moving in the forward direction, and Q minus is the total net amount of negative charges moving in the forward direction, and the total current, total charge will be Q plus minus Q minus, and the current will be Q by T. And definition being, current is defined as rate of flow of charges. It is defined as this is for steady currents. In case of, if it turns out to be like, we can get here based on this definition. Here this Q plus minus Q minus, we can get Q as negative, and time current also we can get it as negative, which implies that if we calculated a current across a conductor in this direction and we got I equals negative, that means we took the direction of the current wrong, and the current is actually moving in this direction and not this direction. For unsteady currents, we take charge across the cross-sectional area to be delta Q, and at time t, then consider change in time as delta t. When the charge is changing, we define current as I equals limit delta t tending to 0 where the change in time tends to 0 and the total time is t plus total time, we take it as t plus delta t, and the current for unsteady flow of charges where a charge is varying, we define current as delta q by delta t. This is the first topic of current, electricity and electric current. The first topic is electrical current. And they gave a few examples here of in lightning we see currents of hundreds to thousands of amperes where ampere denoted by A is the SI unit of current. SI unit of current. In lightning, we see currents of hundreds of thousands of amperes. In case of nerve impulses, we see in our body we see microamperes of current. This is a completion of the first topic. Next topic, electric current in conductors. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charge particles do exist, like in upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 power 22 molecules. These molecules are so closely packed that electrons are no longer attached to individual nuclei. In some material, the electrons will still be bound, that is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are practically free to move within the bulk material. These materials, generally called conductors, develop electrical currents in them when an electric field is applied. Let's read the paragraph again. An electric charge, either positive or negative, will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charged particles do exist, like in the upper strata of the atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 power 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some material, the electrons will still be bound. That is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are practically free to move within the bulk matter. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the current is carried by the negatively charged electron. There are, however, other types of conductors like electrolytic solution where positive and negative charges both can move. In our discussions, we will focus only on solid conductor so that the current is carried by the negatively charged electron in the background of the fixed positive ions. Consider the first case when no electric field is present. The electrons will be moving due to thermal motion, due to which they collide with the fixed ions. An electron colliding with an ion emerges with the same speed as before the collision. Perfect elastic collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction of the velocities of the electron. Thus, on average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So, there will be no net electric current. Let us now see what happens to such a piece of conductor if an electric field is applied. This is a conductor, positive and negative charges. Charges plus Q minus Q put at the ends of a metallic cylinder. The electrons will drift because the electric field created to neutralize the charges. The current thus will stop after a while unless the charges plus Q and minus Q are continuously replenished. To focus our thoughts, imagine the conductor in a shape of a cylinder of radius r. Suppose we now take two thin circular discs of a dielectric of the same radius and put positively charged plus Q over one disc and similarly negative charge at the other disc. We attach the two discs on the two flat surfaces of the cylinder. An electric field will be created and is directed from the positive toward the negative charge. From the positive towards the negative charge. The electrons will be accelerated due to this field towards plus Q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electrical current. Hence, in the situation considered, there will be a current for a very short while before no current thereafter. We can also imagine a mechanism where the ends of a cylinder are supplied with fresh charges to make up for any charges neutralized by the electrons moving inside the conductor. In that case, there will be steady electric field in the body of the conductor. This will result in continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are called cells or batteries that we will study later in this chapter. In the next section, we shall study steady current results from a steady electric field in conductors. Let's read this topic again. An electric charge will experience a force in an electric field is applied. If it is free to move, it will thus move, contributing to current. In nature, free charge particles do exist, like in upper strata of the atmosphere called ionosphere. However, in atoms and molecules, the negatively charged electrons and positively charged nuclei bound together and thus not move free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 power 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound, that is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are particularly free to move within the bulk matter material. These materials generally called conductors. If we consider a solid conductor, then of course the atoms are tightly bound to each other so that the current is carried by the negatively charged electron. There are however other types of conductor like electrolytic solution where positive and negative charges can both move and contribute to electric current. In our discussions, we will solely focus on solid conductors so that current is carried by the negatively charged electrons in the background of a fixed positive ions. Consider first case when no electric field is present. The electron will be moving due to thermal motion due to which they collide with the fixed ions. An electron colliding with an ion emerges with the same speed as before the collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction for the velocities of the electron. Thus, on average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So there will be no net current. Let us see what happens to such a piece of conductor if an electric field is applied. To focus our thoughts, imagine the conductor the shape of a cylinder of radius r. Suppose we now take two thin cylindrical discs of a dielectric of the same radius and put positive plus q distributed over one disc and similarly minus q on the other disc. We attach the two discs on the two flat surfaces of the cylinder. An electric field will be created and is directed from positive towards the negative charge. The electrons will be accelerated due to the field towards the plus q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electric current. Hence, in the situation considered, there will be a current for a very short while and no current thereafter. We can also imagine a mechanism where the ends of a cylinder are supplied with fresh current or fresh charges to make up for any charge neutralized by the electrons moving inside the conductor. In that case, there will be steady electric field in the body of the conductor. This will result in continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are cells or batteries that we shall study later in this chapter. So the next topic is electric currents in conductors. Electric current in conductors. Normally, let's assume there is a charge q, it may be either positive or negative. In presence of an electric field, it will get accelerated in presence of an electric field. It will get accelerated in the presence of an electric field. A charge, if placed in an electric field, will get accelerated. But in the real world situation, we cannot find in most places of the real world we can't find free to move charges. Matter, which contains atoms, which contains nucleus and the electrons, because we can't find them because nucleus and electrons are tightly bound together. Because of that reason, we can't find charges. But there is an exemption given in the textbook, which is the ionosphere, where we can indeed find free to move charges, free charges, but not on Earth. In metals, if we see, in a metallic conductor, in a metal, normally in other matter, electrons are not free to be moved because they are bound by the nucleus. But in case of some special materials, which have free electrons, these materials, normally metals, these materials are what we call conductors. Which have free to move electrons or charges. Normally in this chapter we only study about solid conductors. Solid conductors, the nuclei are tightly bound together. These are nucleus, or the atoms are tightly bound together, or we can say that the positive nucleus will not move even under electric field because there are strong attraction forces between the metal nucleus. Because of that, the current which we study about in this chapter, the current we study about in this chapter in solid conductors is due to moving of free electrons. But for an example of positive charges also contributing current, any charge, if it moves, it will create a current. As such, even positive charges can move and create or contribute to current. Example for positive charge moving can be seen in electrolytic solution. which have both cations and anions, which can contribute to current. If we take, for example, a piece of conductor, a piece or a wire of a conductor, a cylindrical conductor, this is a conductor and this has a radius of r, and this has charges. Electrons are in this conductor. These electrons will not be in a place but will be moving in the conductor, moving all over the conductor. This movement, this energy is provided, this kinetic energy is provided through this kinetic energy for movement is provided due to thermal energy, or the surrounding room temperature, which will give the electrons thermal energy. But this movement, this electron movement due to thermal energy is very random, and if we take, this will be so random that if we take in this conductor, if in a conductor, if we take one electron is moving in this direction, or n number of electrons are moving in, for example, this direction, right side, it is so random that many electrons itself will be also moving in the left direction. So we remember that the net charge equals q plus minus q minus, but since q plus is not moving, it will depend solely on q minus, which is the movement of negative charges or the electrons. This movement is a net movement of q minus is a net movement of electrons here. So if n number of electrons are moving to the right side minus n number of electrons are moving to the left side, and the same minus same will be 0. As such, q will also be 0. If q is 0, I will also be 0. When there is no electric field applied and the electrons are solely moving due to electric field. And the second scenario comes if the charges are under electric field. Let's take the same cylindrical conductor of radius r and attach two discs which are dielectric discs which have a charge of minus q and plus q. Attach them here. We attach them. Now because of this electric field, because we have a positive and a negative charge, the electric field lines will be going from here. positive to negative direction. Due to this electric field, all the electrons inside will all be concentrated in the positive side. Due to this electric field, all the free electrons in the conductor will be accumulated in the positive side, which due to the lack of negative charges in the opposite side, there will be a positive charge. It is not due to movement of charges, but due to the lack of electrons. This concentration, this movement of electrons, because of the short electric field, the short time where electrons move from one end of the conductor to the other, this will create a short time or temporary current. After all the electrons are concentrated over this side, there are no electrons, free electrons, which are able to move to this side. There is no movement of electrons. So when in this state, there is no current. But what if we continue to provide more electrons? Then the electrons will be continuously moving which is what we create a steady current. But in this case, where the conductor is only a piece of a conductor, the current is temporary current, and when all the charges are concentrated at one of the sides, the current will stop. This is for the topic electric current in a conductor. Let's see the next topic, which is Ohm's law. Here they give diagram of a conductor of cross-sectional area A and length L. Here cross-sectional area A and length 2L. Here half of the cross-sectional area and length L. Basically this can be of one material, this can be of another material. Here this one can be of one material and this one can be of another material. And let's go to here, illustrating that resistance equals rho L by A, where rho is resistivity, L is length, and A is area of cross section for a rectangular slab of length L and area of cross section A. Ohm's law, a basic law regarding the flow of currents, was discovered by G.S. Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. Imagine a conductor through which a current I is flowing and let LV be the potential difference between the ends of the conductor. Then Ohm's law states that potential is directly proportional to current, where if we introduce a constant of resistance, V is equal to Ri, where constant of proportionality R is called the resistance of the conductor. The SI unit of resistance is ohm and is denoted by the symbol omega. A resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. It also depends on the temperature as well. Therefore, uh, what does the resistance depend on? It depends on the nature of the conductor, it depends on the length of the conductor, it depends on the area of the cross section of the conductor, it depends on the temperature of the conductor. Resistance is directly proportional to temperature. If higher the temperature, higher the resistance. And if it is also directly proportional to length of the conductor, higher the length, higher the resistance. It is inversely proportional to area, higher the area, lower the resistance. The dependence of R on dimensions of conductor can easily be determined as follows. Consider a conductor satisfying equation V equals Ri or IR to be the form of a slab of length L and cross-sectional area A. In this figure, imagine placing two such identical slabs side by side like this, so that the length of the combination is 2L. The current flowing through the combination is same as that flowing on the either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab. Since the second slab is identical to the first and the same current I flows through the both, the potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs, hence equals 2V. The current through the combination is I and resistance of the combination is RC. RC equals 2V by I, which is equals to 2R. Since V by I equals R, resistance of either the slabs, thus doubling the length of the conductor doubles the resistance. In general, then resistance is directly proportional to length. Next, imagine dividing the slab into two by cutting it lengthwise so that the slab can be considered as a combination of two identical slabs of length L, but each have a cross-sectional area of A by 2. For a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two slabs is I by 2. Since the potential difference across the ends of the half slabs is V, the same across the full slab, the resistance of each of the other half slab is R1. R1 equals V by I by 2, which is 2V by I, which is 2R. Thus, halving the area of cross section of the conductor doubles the resistance. In general, then the resistance R is inversely proportional to the cross-sectional area. Combining equations 3.5 and 3.7, R is directly proportional to L and inversely proportional to A. R is proportional to L by A, and hence for a given conductor, R equals rho L by A, where the constant of proportionality rho depends on the material of the conductor but not on its dimensions. Rho is called resistivity. Using the last equation, Ohm's law reads V equals IR, V equals I rho L by A. Current per unit area taken normal to the current, I by A, is called current density and is denoted by J. The SI unit of current density is R, ampere per meter square. Further, if E is the magnitude of uniform electric field in the conductor whose length is L, the potential difference V across its ends is EL. Using this, the last equation reads EL equals potential difference equals I by A, which is J PL, J rho L, E equals J rho. The above equation for magnitudes E and J can indeed be cast in a vector form. The current density which has been defined as the current through unit area normal to the current is also defined as E and is also a vector. Thus, the last equation can be written as E equals J rho, where rho is conductivity, and J can be written as E by rho or sigma E, where sigma is 1 by rho and is called conductivity. Ohm's law is often stated in equivalent form. 3.13. In the next section, we will try to understand the origin of Ohm's law as arising from the characteristics of drift of electrons. Let's see the topic Ohm's law again, but they gave a slight introduction of George Simon Ohm. We will read George Simon Ohm, 1787-1854, born in 1787, German physicist, professor at Monash. Ohm was led to his law by an analogy between the conduction of heat. The electric field is analogous to the temperature gradient, temperature per distance, where we can denote electric field as potential per distance or voltage per distance, and the electric current is analogous to heat flow. Yes, let's read the paragraph again. Ohm's law, a basic law regarding the flow of current, was discovered by G.S. Ohm in 1828, long before the physical mechanism responsible for the flow of currents was discovered. Imagine a conductor through which a current I is flowing, and let V be the potential difference between the ends of a conductor. And Ohm's law states that V is proportional to I and V equals Ri, where constant of proportionality R is called resistance of conductor. The SI unit of resistance is ohm and is denoted by the symbol rho, omega. The resistance R not only depends on the material of the conductor but also depends on the dimensions of the conductor. The dependence of R on the dimensions of the conductor can easily be determined as follows. Consider a conductor satisfying equation 3.3. Imagine placing a slab of length L and cross section A similar to the figure which we took. Imagine placing two such identical slabs side by side so that the length of the combination is twice the individual length, or 2L. The current flowing through the combination is the same as the current flowing on either of the slabs. If V is the potential difference across the ends of conductor or the first slab, then V is also the potential difference across the ends of the second slab. Since the second slab is identical to the first slab and the same current I flows through the both, the potential difference across the ends of the combination is clearly sum of potential difference across the two individual slabs and hence equals 2V. The current through the combination is I and resistance of the combination RC equals 2V by I, which is 2R. Since V by I equals R, the resistance of either the slabs, thus doubling the length of the conductor, doubles the resistance in general. In that case, we can say that resistance is generally proportional to length. R is directly proportional to length. Next, imagine dividing the slab into two by cutting it lengthwise so that the slab can be considered as a combination of two identical slabs of length L, but each having a cross-sectional area of A by 2, which is half of the original area. For a given voltage V across the slab, if I is the current through each of the two half slabs is I by 2, Since the potential difference across the ends of the half slabs is V, the same as across the full slab, the resistance of each of the half slabs is R1 is R1 equals V by I by 2 and 2V by I equals 2R. Thus, having the area of cross section of a conductor halved doubles the resistance. In general, yes, the resistance is inversely proportional to the cross-sectional area. Combining R is directly proportional to L and R is inversely proportional to A, we get R is proportional to L by A. Combining equations and with a proportionality constant of rho, which is resistivity, we can say that R is equal to rho by L by A, rho times L by A, where constant of proportionality rho depends on the material of the conductor but not on its dimension. Rho is called the resistivity. Using the last equation, Ohm's law reads V equals I into R equals, where we substitute value of R, which is rho L by A times I, current per unit area, taken normal to the current. I by A is called current density and is denoted by J. The SI unit of the current density is ampere per meter square. Further, if E is the magnitude of the uniform electric field in the conductor whose length is L, then the potential difference across its ends is EL. Using this last equation, we can get EL equals J rho L, which we got from V equals I by A times rho by L, V equals IR. The above relation for magnitudes E and J can be cast in a vector form. The current density, which have been defined as a current through unit area normal to the current, is also directed along E, the electric field, and is also a vector. Thus, the last equation can be written as E equals J rho or J equals rho E, where sigma equals 1 by rho is called the conductivity. Ohm's law is often stated in a equivalent form. In addition to section, we will write, okay, this is the Ohm's law definition or the Ohm's law statements. Let's see the topic once more. Third topic of current and electricity. Ohm's law. Basically, the statement is across the two ends of a conductor carrying current I and having a potential of V at constant temperature and pressure, I is directly proportional to V, or in other words, V is directly proportional to I. This is a basic statement of Ohm's law with V equals IR, or IR, or where R is the proportionality constant, which we call resistance for a conductor depends on one, nature of the conductor, as if it has more free electrons and if it can allow more flow of electron. 2, length of conductor. 3, area of cross section. 4, of conductor. 4, it is temperature of conductor. As for how the proportionality or how this resistance depends on length and area, we can prove it by taking, for example, let's take a slab of area of cross section A and length L. Yes, length L and area of cross section. This is a slab of a conductor. Then we know that V equals IR. This is Ohm's law statement. Let's call this conductor as this piece of a conductor, exact same. Let's call it the B conductor, or yes, B conductor. Let's call it the B conductor just for naming sake. It does not represent anything. This B conductor, let's take 2 of these B conductor, same, of length L and cross-sectional area A, with the total length being 2L, and we connect them in this manner, series manner. So we know that in this case the current will be the initial current in the single slab, in the single B conductor with area A and length L. Here it will be equal to the current in this conductor as well. The current in both these conductors will be same. Now let's see area of cross section. Area of cross section is same itself. Now let's see voltage or potential. Here we know that V1 in the single case or the single B conductor will not be equal to V2. Here a single slab has V potential. Here there are 2 slabs, so each having V potential. So V of this case, which let's call it Vp, equals 2V. Let's substitute the values. I1 equals I2, or IB equals I. So we know that V equals IR and R equals V by I. If we substitute V value, which is 2V by I yes 2V by I, which is not the resistance, but let's take it the resistance. Let's take this is the resistance for the B case. Here in this case, let us take it as B, and the initial for a single slab the resistance is R, and RB, this is not RB, for R it is V by I, and for RB it is 2V by I, which we can write it as 2 times V by I or 2 times R. So here when we added or connected two slabs in this manner, the resistance doubled. RB equals 2R. So the resistance is double of the initial resistance. In such a case, we can derive a relation between resistance and the length, where we can say R is directly proportional to the length. Because here we saw when length increased from 1L to 2L, resistance also increased, resistance also doubled. So you can say R is directly proportional to L. That does not mean if length doubles, resistance will also double. No, just means that it is proportional. And the next case, let's take case 2 for area, for the relation between area and resistance. Let's take two half slabs of area A by 2 and attach them in a parallel manner. Here as well the area is A by 2. In this case, potential in this side will be equal to this side, so the potential in both of the slabs will be equal. Potential will be equal. But in case of current, it will be the single individual for the one, it will be I by 2. The current will be halved for each of the conductors. If we apply the formula, V equals IR and R equals V by I, then R equals V by I by 2, 2 will come up. R equals 2 times V by I, which is nothing but R2 equals 2R1. So here as well, when we reduced slash decreased length, decreased area, the resistance increased. So we can say that R is inversely proportional to A. When A increases, R decreases. When A decreases, R increases. And based on the two relation of R is directly proportional to L and R is inversely proportional to A, we can derive that R is proportional to L by A, and we can introduce a proportionality constant R equals rho L by A, where rho is resistivity depends only on the, along with temperature, but only on the nature of the material, and not the dimensions of the conductor. So in this equation, we know the Ohm's law equation or statement V equals IR. In this equation, we substitute the new R value we got from here, we substitute in this equation. We get that V equals I rho L by A. V equals I rho L by A. From the previous chapter, we know that potential is electric field times distance, or we can inversely write it as E equals minus d by dV by dr. This we can write it as V equals EL. Now substitute this value in this equation. We will get that EL equals I by A rho L. L cancel. We will get it as E equals I by A rho. And we can define, we have a new definition for I by A, which I will define it right now. Current density. Current density, it is the current passing normally to the area of cross section of a conductor this is known as current density, denoted by J. Formula, it is a scalar quantity, and formula is J equals I by A, and in this equation we can substitute the value for I by A, which we will get it as E equals J rho. This, if we want the value of J, we can write it as J equals E by rho. Rho, we can define another property here of conductivity. Conductivity, which we can define as, which we can represent as sigma, and which we can define as, it is inverse of resistivity. So sigma equals 1 by rho, in which case here we have 1 by rho, which we can write J or capital J. J equals E sigma, or J equals sigma E. This is the final answer for current density. With this, we can end the topic Ohm's law. at least partially. Drift of electrons and the origin of resistivity. As remarked before, an electron will suffer collisions with heavy fixed ions, but after collision it will emerge with the same speed but in random directions. If we consider all the electrons, their average velocity will be 0 since their directions are random. Thus, if there are n electrons and the velocity of the ith electron, where I equals 1 like natural numbers, at a given time is Vi, then 1 by n sigma n, where I equals 1, Vi, or basically the net velocity for all the electrons till the considering all the individual electrons will be 0 if we do the sum. This is basically sum of all the electrons, sum of the individual velocities of all the electrons. Consider now the situation where when an electron consider now situation when an electron is present, electrons will be accelerated due to the field. Consider now the situation when an electric field is present, where the conductor or a charge is under an electric field. Electrons will be accelerated due to this field by A equals minus E by M, where E is the electric field, minus E is the charge of electron, and M is the mass of an electron, where minus E is the charge of an electron and M is the mass of an electron. Consider again the ith electron at a given time t. This electron would have had its last collision sometime before t, and let Ti be the time elapsed after the last collision. If Vi was its velocity immediately after the last collision, then its velocity Vi at the time t equals this one. Since starting with its last collision, it was accelerated with an acceleration given by this equation. For a time interval Ti, the average velocity of the electron at time t is the average of all the V initials. The average of V initials is 0, since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of electrons do not occur at regular intervals but at random times. Let us denote by tau the average time between successive collision. Then at a given time, some of the electrons would have spent time more than tau and some less than tau. In other words, the time Ti will be less than tau for some and more than tau for others. As we go through the values, I equals 1 from 1 to n. The average value of Ti then is tau, known as relaxation time. Thus, averaging equation 3.16 over the n electrons at any given time gives us the average velocity Vd. Vd equals Vi average minus E capital E by M and tau, which we can define as minus E by M times tau. This is the last result. This last result is surprising. It tells us that the electrons moves with an average velocity which is independent of time. Although electrons are accelerated, this is the phenomenon of drift and the velocity Vd, or drift velocity. In this case, the electric field is in this direction. Electric field is in this direction, so electrons will move in this direction. This moment or drift is what we call drift velocity, and this is the delta x equals Vd times delta t. Current in a metallic conductor. The magnitude of the current density in a metal is the magnitude of charge contained in a cylinder of unit area and length Vd. Current in a metallic conductor. The magnitude of current density in a metal is the magnitude charge contained in a cylindrical unit of area and length Vd. Drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Let's read the statement again. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Then, because of the drift, in an infinitesimal amount of time, delta t, all electrons to the left of the area at distances up to Vd times delta t would have crossed the area. If n is the number of free electrons per unit volume in the metal, then there are n delta t magnitude of drift velocity times a such electrons. Since each electron carries a charge minus e, total charge transported across this area A to the right in time delta t is minus NEA Vd delta t. E is directed towards the left and hence the total charge is transported along E across the area is negative of this. The amount of charge crossing the area A in time delta t, by definition I delta t, where I is the magnitude of current, hence I delta t equals NEA Vd delta t. Substituting the value of Vd from equation Q, we will get I delta t equals E square A by m tau n delta t. By definition of I, the magnitude of current density by I equals current density times A. Hence, from the equations 3.19 and 3.20, we get current density equals Ne square tau by m times magnitude electric field, this vector, if parallel to E, and hence we can write equation 3.21 in the vector from J equals Ne square by m tau E. Comparison with equation 3.3, 3.13, which is current density equals sigma E shows that equation 3.22 is exactly the Ohm's law. If we identify the conductivity sigma as Ne square tau by m, we thus see that a very simple picture of electrical conduction reproduces Ohm's law. We have of course made assumptions that tau and n are constants independent of E. We shall in the next section discuss the limitations of Ohm's law. This is the topic. Of course, let's see the topic again. Drift of electrons and the origin of resistivity. An electron will suffer collisions with heavy fixed ions called lattice, but after collision it will emerge with the same speed but in random directions. If we consider all the directions of electrons and sum of their individual velocities, we will get that the net velocity will be 0. Consider this figure a schematic picture of an electron moving from A to B through repeated collisions and straight line travel between collisions, full lines. If an electric field is applied as shown, the electrons end up at B, dotted lines, a slight drift in direction of the opposite. This is when an electric field applied. If without electric field, it would have gone in this way, but the dotted line represents the electric field, where the electrons will slightly move in this direction. Consider now the situation where electric field is present and electrons will be accelerated due to the field, and the acceleration is minus em by m, minus e by m, which I will derive it. Yeah, minus e is the charge and m is the mass of an electron. Consider again the ith electron at a given time t. This electron would have had its last collision, and they are defining tau here, relaxation time. This electron would have had its last collision sometime before t, and let ti be the time elapsed after its last collision. If vi was its velocity immediately after the last collision, then its velocity vi at time t is vi equals vi, where it is plus minus e by mt. Starting with its last collision, it was accelerated with an acceleration given by equation 3.15 for time interval ti. The average velocity of electrons at that time is average of all the vi's. The average velocity of the electrons at time t is average of all the electrons. This vi is the velocity of electron just after its collision. Wait, it is the this is the velocity before collision, not after collision. This is velocity before collision, and this vi is the total average velocities of all the electrons. Starting with its last collision, after this collision, vi is before collision. After collision, it will get accelerated and the average of vi's is 0, since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of the electrons not occur at regular intervals but at random times. Let us denote by tau the average time between successive collision. The time difference is different, so we take an average, which we call it as relaxation time. We get v drift velocity equals vi average minus the result is surprising. It tells us that electrons moving with an average velocity is independent of time. Although electrons are accelerated, this phenomenon of drift and velocity Vd in equation 3.17 is called drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Then, because of the drift in an infinitesimally amount of time, delta t, the drift caused in some very small amount of time, all electrons to the left of the area at distance is up to this is basically using the very basic velocity equals distance by time. As such, distance where they took as delta x equals velocity, which is drift velocity, times time taken or change in time. Would have crossed the area. Vd times delta t would have crossed the area. If n is the number of free electrons per unit volume in the metal, then there are Vd delta t is the distance crossed by the electron, and if there are n number of electron in a per unit volume of area, then we can get that in a metal there are n times the time or change in time times drift velocity times area. Since each electron carries a charge minus c, the total charge transported across this area to the right in time delta t is minus ne a delta vd times delta t. E is directed towards the left, and hence the total charge transported along E across the area is negative of this. The amount of charge crossing this area A in time delta t is by definition I delta t, where I is the magnitude of current. So n delta t or distance this relation giving the number of electrons, and if we introduce charge with these are the number of electrons, if we need a charge of such electrons, need to multiply it with minus c, we'll get this equation. And with the equation, this is the charge q equals minus ne vd delta t. Ne vd delta t, right? Yes. Right. Ne vd delta t times a. This is the formula for Q, but if we take current equals Q by T. So I times T should be equal to Q. That is why here they substituted I delta T equals plus NEA delta drift velocity times delta T. And here this will be the equation. Okay. Okay, let's see. This is the drift of electrons. The next topic which is topic number 4, I believe. Yes, topic number 4. Topic number 4, drift of electrons and origin of resistivity. If we take a conductor with an electric field, normally without an electric field, let's assume without electric field, we saw that the total velocities of the electrons, total net velocity net of all the electrons will be 0. We know this. This is when there is no electric field. Because if we take an electron is moving in this direction, let's say there are n number of electrons moving in this direction, there will also be n number of electrons moving in this direction, and based on in the first topic we learned that Q minus equals total net amount of electron moving in the forward direction or a chosen direction. So Ne minus minus Ne minus will be 0. The total charge here will be 0 and the velocity net also will be 0. And let's take if under electric field, this is an electron, let's assume this is electric field, it will experience an acceleration towards this direction. This acceleration is termed as minus E times E by m, which we can derive by, we know that force according to Newton's second law, force equals F equals ma, and we know that electric field intensity is force per Q, force by charge, and force due to an electric field is Q times E, and when we equate them, both are force, so we can equate them, we will get that ma, mass into acceleration, is equal to Q times E. We know that the charge of the electron, we are taking an electron here, we can write ma equals minus E times electric field. In such a case, acceleration will be minus E times E by m, where E is the charge of electron, minus E is the charge of electron, and capital E is the electric field, and m is the mass of the electron. This is the derivation, and velocity average, we can take it as 0 of all electron, all electron. And based on the next was relaxation time, as electron will be colliding with the positive charges. Let's assume this electron has a velocity of v, magnitude v. This electron will also have a velocity of magnitude v after collision. This electron will go collide with the nucleus and it will be bounced, and this bounce is perfectly elastic so that the magnitude of velocity is maintained but the direction is changed. This is how normally the electrons will be moving around in the metal or conductor. And the time, let's assume this electron will again collide with one more nucleus here, and it will again change direction to this side. As the collision is perfectly elastic, it will maintain the magnitude of velocity, but direction will be again changed. Let's assume this is the first collision and this is the second collision. The time at before collision is t equals 0, let's assume, before the first collision, and t after the first collision equals t1. The time after the first collision or at the time of the first collision is t equals t1, and time at the time of the second collision, let's assume it is t2. So this time where there is no collision, the gap between two successive collision, the time interval between two successive collisions is represented by tau, but this is not what we call relaxation time. As for example, this electron took a time of 2 seconds, it had a time of 2 seconds, let's assume, before collision. It took 2 seconds, but in another case, one more electron only had time of 1 second before collision, 1 second of the gap or time interval between two collisions. So one electron may have higher time interval, whereas another electron, A electron might have higher time interval, but B electron might have lesser time interval. In such a case, we take the average time interval between two successive collisions or successive collisions is represented by tau and is called relaxation time. This is the average relaxation time. We represent it as tau. Based on the equation if we take Newton's equations of linear motion, v equals u plus at, in this equation we can substitute the electron values where Vd is the drift velocity, Vi average, which is the average of all the electrons, Vd is the drift velocity. What is this drift velocity if you want to know? Let me explain. Drift velocity is nothing but if there is an electron moving, this is collision, then one more collision and one more collision. This is the normal path of an electron in a metal conductor. This is without electric field. If this electron is experiencing a electric field, Let's not take that direction. Let's assume it is experiencing an electric field of this direction applied in this direction. So this electron will feel an acceleration towards this side. This electron will be accelerated towards this side. So the path, it should be like this. It will be drifting. Like this. When the original path was supposed to be like this and going this way, due to the drift or the acceleration applied due to the electric field, the electron will drift towards this side. It will be slightly drifting towards this side. This is what we call drift velocity. The amount of drift or rate of drifting of the electron per unit time, we can name it as drift velocity. We represent it by Vd. And as for getting the equation for Vd, we take Vd equals Vi average, which is the average velocity of all the electrons moving in random directions, plus acceleration times time. Here we already know that this is 0. So Vd equals V drift equals acceleration minus E times m. This is minus E times m times, you can take the time as relaxation time. Vt equals minus E by m times tau. This is the relation for or derivation for drift velocity. The second derivation is for current. Let's do it in the next page itself. In a conductor, let's assume this is a conductor of length L and area of cross section A, and this conductor has an electric field in this direction, so electrons will be moving in this direction. In such a case, let's assume N on this end this n is the total number of electron in that piece of conductor. Capital N is the total number of electrons in that piece of conductor, and small n be the total number of electron per unit volume of conductor. So basically N equals N per volume, total volume of the conductor. So in this conductor, let's assume in this is a cross-sectional area. Let's assume electrons are passing through this area. This we can, as for how much distance they are moving through, we can take it as drift velocity times time. Drift velocity times time. We know that this is basically a Vd equals, or not Vd, but Yes, velocity is equal to distance by time. So if you want to find how much distance the electron are moving, distance equals velocity times time. So we can write it as Vd times delta t, magnitude of Vd. So the distance moved electrons, or let's take it as n number of volume, this is the volume density of electron moving at distance of Vd times delta t in an area of A. This is the total number of electron. In the conductor. How that is true, meaning if you want to know how that is true, I told you that n equals n by v. So substitute in this equation, where n we can write it as where n by v, substitute times Vd times delta t and times area. This we know that Vd times delta t, which will get the distance. So this will be n by v times x a. When we know that area times length equals volume, so nv times volume cancel, so we get n, the total number of electrons. So we can say that n equals the n times the small n, volume density, times drift velocity times time taken times area. This is the total number of electron. If these are the electrons, what is the charge of electron? It is, we can write it as minus e. We can write the charge of electron as minus e. So if we multiply this, we will get that minus e times delta Vd times delta t times a, of course, times n. This is the charge of all the electrons. If all the this is basically n times minus ne, which is the charge of all the electrons, and this charge we can write it as I delta t, because q by t equals I, and it equals q. So I delta t equals minus en delta Vd delta t times a. Delta t cancel, and I equals minus en delta Vd times a. This is the current formula, which we can simply denote as I equals Vd VDE and A Vina, and we can substitute Vd value here. We got Vd equation, I equals E electric field by M. This is Vd times area times En, and if you want to denote an expression of current density here, we can divide both sides by A. I by A, which is equals to current density, equals here E square E by M times n, where a into 1 by a got cancelled. This is NEEE by m. This will be current density. Wait a second. Yes. The formula here includes tau. But if you just arrange this equation in a different manner, if you arrange it in n e square tau, this is tau, but it has j. Tau n e square tau times electric field by m, and this current density relation we can relate to J equals sigma E, where sigma is conductivity. So based on this, if we see both of them, we can understand that sigma equals n e square tau by m. For remembering, we can remember it as sigma equals NEET, NEET by m. And as for rho, which is inverse of tau, inverse of sigma, we can get it as m by NEET. Relation between, we got three important formulas here of current equals negative of VDENA, Vina, and Q this both we can write it as L. If we write it as L, we can get that Q equals we can take charge as E itself instead of taking minus EN LA. This is the charge formula, which we can write it as Q equals ANEL and L. This is one important formula, and this is the second important formula, and this is one more formula of importance, this one, and value of sigma and rho. This is basically completion of, as for the electron drift, and also as for what is resistivity. Resistivity it is defined as nature of material to resist the flow of electron in case of conductors, in case of solid conductor, or charges in case of other materials. Resistivity or resistance is due to the, when electron is moving in this direction, if there is a positive nucleus, it needs to change in direction. This continuous collisions which is what cause resistivity. as for the next topic. An example, estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 times 10 power minus 7 meter square carrying a current of 1.5 ampere carrying current of 1.5 ampere. Assume that each copper atom contributes roughly one conduction electron. The density of copper is 9 into 10 power 3 kg per meter cube and its atomic mass is 63.5 U. Compare the drift speed obtained above with thermal speeds of copper atoms at ordinary temperature, speed of propagation of electric field along the conductor which causes the drift motion. Solution for A is to find the average drift velocity. We should use the equation Vd equals I equals Vd ENA, where we will get Vd equals I by NEA. Now the values, if we substitute, we will directly get the average drift velocity. They did not give the electron density, but they gave that each copper atom contributes a single electron and they gave the density of copper. So we know that n, the small n value, it's equal to n equals to capital N by V. In the density we can find the total number of electrons and divide it by volume of the conductor, where mass by volume. Since 16 to 10 power 23 copper atoms have a mass of 63.5 grams, N equals 6 into 10 power 23 by 63.5 times 9. The formula density rho equals mass by volume and they gave mass of the conductor, which is 9 to 10 power 3 kgs or 900 kg. We took the mass of the conductor to be electron equals 1.6 into charge of electron equals 1.6 into 10 power minus 19 coulomb. Area which they gave as 1 into 10 power minus 7 meter square. I equals 1.5 ampere. Density of conduction electrons N is equal to the number of atoms per cubic meter, assuming one conduction electron per copper atom is reasonable from its valence electron count of 1. A cubic meter of copper has a mass of 9 into 10 power 3 kg. So 6.0 into 10 power 23 copper atoms have a mass of 63.5 grams. So we are calculating yes, this is the number of moles of copper atoms. Since each copper is producing giving only one electron, 1 times 9 into 10 power 6 by 63.5 gives the moles of electrons, and if we multiply this with 6 into 10 power 23, which is the Avogadro's number, we will get the total amount of electrons. We get the total amount of electrons per meter cube. Yes, since we took, this is actually the density, so this will have a SI unit of kg per meter cube. So it will leave this many electrons per meter cube. Yes. Drift velocity equals, we got this value, so substitute in this in the above equation. Where Vd equals I by NEA, Vd equals 1.5 by 8.5 times, yes, whatever. Vd equals 1.1 times 10 power minus 3 meter per second, or 0.11 times 11 into 10 power minus 4 meter per second. At a temperature T, the thermal speed of a copper atom of mass m is obtained from, it is smaller than half mv square and greater or equal to 3 by 2 times kBt, where kb is a Boltzmann constant, and it's just typically of the order delta kb times T by m, where kb is the Boltzmann constant for copper at 300 Kelvin. This is about 2 into 10 power 2 meter per second. This figure indicates the random vibrational speeds of copper atom in a conductor. Note that the drift speed of electrons is much smaller, about 10 power minus 5 times the typical thermal speed at ordinary temperature. An electric field traveling along the conductor has a speed of an electromagnetic wave, namely 3 into 10 power 8 meter per second, the drift speed is in comparison extremely small, smaller by the factor of 10 power minus 11, which is 10 power minus 3. In example 3.1, the electron drift speed is estimated to be only a few millimeter per second for currents in the range of few amperes. How then is current established almost the instant a circuit is closed? The question: if the speed of the drift velocity is so small, when you light the switch or turn on the switch in your house, when in the next instant the bulb will turn on. Why? The electron drift arises due to the force experienced by electrons in the electric field inside the conductor. But force should cause acceleration. Why then do the electrons acquire a steady average drift speed? If the electron drift speed is so small and the electron's charge is small, how can we still obtain large amount of current in a conductor? When electron drift in a metal form from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? Are the paths of electron straight lines between successive collision with the positive ions of the metal in the absence of electric field? To first case, in the absence of electric field and in the presence of electric field. Answer to the first question: the electron drift speed is estimated to be only a few millimeters per second for currents in the range of few amperes. How then is the current established almost an instant circuit is closed? Solution: electric field is established throughout the circuit almost instantaneously with the speed of light, causing every point at local electron drift a local electron drift. Electric field is established throughout the circuit almost instantly with the speed of light, causing at every point a local electron drift. Establishment of a current does not have to wait for electrons from one end to the conductor traveling to the other end. However, it does take a little while for the current to reach its steady value. This is a circuit, and here we have a positive to negative, positive to negative, positive to negative, and positive to negative electric field. Here electron will move this side, this electron here will again move this side, here as well the electron will move this side, here as well the electron will move this side. Every electron in every part of the conductor will experience an electric field, so the electron may be wherever it is will experience this electric field. Due to that reason, all the electrons will have a drift velocity almost at the same time. Due to this, the current is almost instantaneous. Each free electron does accelerate, increasing its drift speed until it collides with positive ion. Wait, let's read the question first. The electron drift arises due to the force experienced by electrons in the electric field inside the conductor, but the force should cause acceleration. Why then do the electrons acquire a steady average drift speed? Each free electron does accelerate, increasing its drift speed until it collides with a positive ion of the metal. It loses its drift speed after collision but starts to accelerate and increases its drift speed again, only to suffer a collision again, and so on. On the average, therefore, electrons acquire only a drift speed. I'll be pausing the stream for some time. It will be break time.
was nothing like